Hello everyone, I'm Gay Yehill, and welcome to the Cosmic Lounge at JPL on Ustream. Once in a while, every time there is a timely story, we open up our studios and bring in some of our scientists to talk about the story and to answer some of your questions. So the topic today is YU55. It's an asteroid that is coming to Earth, flying by about 9/10 the distance of Earth and the Moon, and it's about 400 meters in diameter, so quite large, about the size of an aircraft carrier. This is coming by on November the 8th, and it will be flying by the Earth, and astronomers and observers will be watching for it. To fill us in on it right now is the principal investigator, Lance Benner. Here's his story.
2005 YU55 is going to make a very close approach to the Earth on the night of November 8th, 2011. At that time, its distance from Earth will be just under 9/10 of the Moon's distance away from us. It's going to be moving very rapidly as it traverses the sky near the Earth on November 7th, 8th, 9th, and 10th. In effect, it'll be moving straight at us from one direction, and then it'll go whizzing by and straight away from us in the other direction. So its motion across the sky will be close to 180 degrees over the course of less than 2 days. 2005 YU55 cannot hit Earth, at least over the interval that we can compute the motion reliably, which extends for several hundred years. It made a close approach to Earth about 18 months ago. In April of 2010, colleagues of ours at Arecibo Observatory were able to observe this asteroid using the radar facility at Arecibo. And they were able to obtain radar images that showed that this object is about 400 meters across. On November 8th, 9th, 10th, we'll be observing it again, this time with both the Arecibo telescope and with the Goldstone telescope here in California. This is the closest approach by an asteroid that large that we've ever known about in advance. The radar telescopes that we use to observe asteroids are very large radio dishes. The Goldstone telescope is 70 meters, which is 240 feet across, so it's truly enormous, and Arecibo is even larger still. The Goldstone telescope has a new radar imaging capability which has just become available that will enable us to see much finer detail than has previously been possible. And depending on how we transmit the signal, we can get different types of data. It shows us how big it is. It can show us features on the asteroid. It can tell us information about the asteroid's rotation period. We should be able to tell much better with these new observations that we're going to do.
All right, with me now is Marina Brozovic. She is a co-investigator with Lance and also a member of the radar team. And Marina is going to fill us in on exactly how do they get this data and this information about an asteroid just like YU55. So first of all, just to reiterate, a question that we are getting over and over in emails, on Twitter, and in chat: will this asteroid hit Earth? And we did hear it once before, but just to reiterate.
No, absolutely it is not going to hit us. We have very good idea about its orbit for the following 100 years, and there is no chance of impact. And we believe with these measurements, upcoming measurements at Arecibo and Goldstone, we believe that we are going to remove this threat even further. Probably centuries, for many centuries, we'll know exactly where this object is going to be.
This is such a terrific opportunity. This is a time where it's a very or fairly large, an average size asteroid, 400 meters. You know where it is. You know when it's coming. It's an excellent opportunity for observers to be standing by, ready to watch, ready to learn from it. So you watch and learn using radar. And exactly how do you do that?
Yes, so we are going to study this asteroid by using both Arecibo radar and Goldstone radar, and we are going to have a small video of showing exactly how do we learn about asteroids based on the radar images.
All right, so
we're
we'll go
going to
ahead
show
and load
straight
that video.
Okay, so I'm going to tell you exactly how we use radar to learn about asteroids. Currently, we have only 2 planetary radars in the world. One is Goldstone in California, and the other one is Arecibo in Puerto Rico. So scientists use radar to ping asteroid and to learn its exact location and line of sight velocity. This allows us very precise orbital calculation. And we also use radar to obtain high-resolution radar images of these asteroids that knows to be hundreds of thousands, even millions of kilometers away. So imagine that radar is a very simplified, like flashlight. But instead of the visible light, it's transmitting microwaves. And you see microwaves are right between somewhere infrared and radio waves. And so we are transmitting these microwaves. They're moving at the speed of light. They're bouncing off the asteroid. We have this echo, and this radar echo is containing information both about surface features of the asteroid as well as its rotation. Here I'm showing you just how the really radar image looks like, and I'm going to tell you very simplified, this is not your regular, this is not your optical image. So here is how it works. We transmit the beam, and we time the round-trip time to the asteroid and back. We know the speed of light. That's how we know exactly the distance from the radar to the asteroid. This pink line shows you that. Notice that the front of asteroid is closer to the radar than the sides. We also have the information about rotation. If it's rapidly rotating asteroid, the echo is wider. If it's slowly rotating asteroid, the echo appears narrower. Once again, I'm repeating in a summary, what you saw on that radar image, what we see on the horizontal axis is really the width of the echo in frequency. And on the vertical axis, you're measuring how far each little feature on that asteroid is far away from radar. Here is side-by-side example. This is how you would see it with your camera. You take a snapshot with your camera, and then here's the radar image. And notice that radar is taking the image exactly in the perpendicular plane to your regular camera. Again, here I'm showing you how if the asteroid was rotating faster, the echo would appear wider. And again, if you are looking at the asteroid that's rotating relatively slowly, then it appears narrower. Here is again, notice that in this plane, in this radar line of sight, you have features from the northern hemisphere lit by radar and the southern hemisphere lit by radar really superimposed. Imagine if this were Earth. If this were Earth, this would be its radar image. You would not know which land mass belongs to the northern hemisphere and which one belongs to the south hemisphere, because it's in this completely different, it's in this perpendicular line of sight. But luckily, we have ability to untangle this so-called north-south radar ambiguity. But that's another story.
So, we're so entrenched in seeing things optically with our eyes because that's how we take pictures with our own cameras. I mean, that's how most people see things. And that is how much light comes into the aperture, how much light so you can visually see it. But you mentioned that you bring your own light. It's like having a flashlight. Can you explain how that works?
So optical telescopes, they really depend on a sunlight being reflected from the object.
Right.
But in our case with the radar, we bring our own flashlight. So imagine that this is the radar and this is the asteroid, and so we'll be shining this radar beam at the asteroid, and it's active technique, and we are bouncing off the beam of light and then receiving the echo back, and then the computers are processing this received data, and we finally build an image. We build an image of that asteroid.
So if you are at Palomar Observatory, you have to wait until nighttime to be able to see the stars, to see an asteroid. In a case like you, where you bring your own light.
Yeah, you're a daytime, you get to be daytime astronomer and you get to sleep at night. So
very good.
So yes, well, we also have night tracks. A lot of times, well, it all depends when really the object is crossing the beam, the telescope beam, the radar beam. And Goldstone, for instance, it has 80% coverage of the sky, so we can track objects for many number of hours, 7-8 hour tracks. And at Arecibo, we wait also for the object to come into its beam, which is much kind of, Arecibo can steer, but it's much more powerful telescope. So it really, we schedule our tracks dependently on availability of the time, depends basically how the telescope has available time, and obviously when you can see the object.
But then you have that much more observation time. You don't have to wait until nighttime to be able to see things, and you have that much more opportunity to see things, don't you?
Yeah, well, it's comparable. You know, just I was just at Palomar and I spent 13 hours at the telescope, so that's quite a long time to observe something.
All right. Well, as I said, we are here to answer your questions via chat, as well as some of the questions that were sent to us via email and Twitter and Facebook. So the first question is from Jeff. It was an emailed question. Will 2005 YU55 be visible in the night sky as it passes Earth?
You will need a small telescope. So this is still very small object. 400 meter is, I would say, a moderate size asteroid, but it's still small, very far away.
Okay.
So you need about at least 6-inch telescope in order to be able to observe it, and you'll see it as this like buzzing really, really fast across the sky.
And because it is so quick, I mean, you would probably, even though you do have a telescope, would have to know exactly where to look. You would have to have the coordinates, wouldn't you?
Yes. The coordinates for this object are widely available on many amateur astronomers' websites, Sky and Telescope, or anything like that. So I'm sure that they have very detailed predictions. Where can people point their telescopes to?
Okay, here's a question. Now, this one's from the chat. It's from Lortendella, and where is the best time and location in California to view?
For that, I think it's best to check with Sky and Telescope for optical observations, or check with probably space weather. All of them are going to have detailed information much better than I can give you.
Okay.
So I only know when my radar, where our radar tracks are scheduled, but
we should be able to see it.
Absolutely, yes,
On
absolutely.
November 8th, I'm told, is the best time.
November 8th becomes a nighttime object, and that's the time when you can see it.
But you start observing even sooner than that, don't
Yes, our actually first radar track is scheduled already this Friday. So in the morning, we're going to be observing it with gold sun for about 2 hours.
Right, I was told that it's coming in the direction
from the
sun, so anybody trying to look at it wouldn't be able to see it anyway because it's looking directly into the sun.
Yes, it's daytime.
Okay, here's another question from, I think it's Talk Turtle. I'm not sure. Perhaps you would be able to answer this. Does the UNESCO tsunami exercises and the first ever nationwide emergency broadcast system indicate there is some concern of an impact?
I'm absolutely sure that it has nothing to do, because there's no chance of impact. So whatever they're doing, it has nothing to do with this asteroid.
All right. I ate your neighbor is the other handle. Does the USA have a monopoly on radar or any other observations?
Well, these two radars happen to be in United States territory, but our CBO is accepting observing proposals from. I believe that it can be international collaboration, but yeah, for now the radar community is really small and it's localized in the United States. But that doesn't mean that interest for radar observations are not there, and that other places in the world are planning maybe there to expand their capabilities.
And one final question from the chat is SJD394. If the asteroid was to hit the moon, what would happen?
I'm not familiar with that asteroid, and I'm sure that Don Yeomans can answer better that question than I can. I absolutely am not familiar with that object.
But like you, by the same token that you know that it won't hit Earth, because you've been able to track it.
Was this the same object?
Yes, they're asking for this, if this asteroid was to hit.
You said SJ.
Oh, no, that's their handle.
Oh, I'm sorry. Yes, I misunderstood. I thought we are suddenly talking about some new asteroid.
No, this is the person who sent the question.
Oh, I'm sorry.
So if it were to hit the moon, and there's...
No, there's absolutely no chance that it's going to hit either Earth or moon. So we know very precisely where the subject is going to be for, as I said, at least another 100 years. And there are no chances of impact.
And how are you able to do that? How are you able to look ahead for several hundred years exactly where this asteroid was going to go?
Well, this asteroid was discovered in 2005, and it's been 6 years. We built a very long observational data arc about this object. And also we have radar measurements, and radar measurements are very precise. You get to know where the object is within less than 10 meters, and you measure line of sight velocity up to 1 millimeter per second. So that automatically solidifies your orbit, and that's why you are able to make very detailed predictions in the future for this object, we usually are able to say several centuries where the object has been and where it's going, because we just build a long number of observations, and we keep updating that orbit and keep building and building better orbit. So eventually, you're very certain where it's going to be. Your error is very small, and so there is no chance of anything surprising you.
And with the information you'll be getting from this observation,
Yes.
you'll probably
That
be
is-
able to refine it even more.
Again, we are going to know where this object is within 4 meters. And again, measuring line of sight velocity up to 1 millimeter per second, that is very strong measurement. So you will be able to extend where this object is going to be very precisely much further in the future.
All right. So we took care of a couple of questions, and let's go back to talking to Marina about what she does. So you get your observations, you get your data, and then what do you do with it? How do you make sense of it? And we've got a video that you pulled together of another asteroid.
Yes.
It's KW4?
It's KW4.
Tell us about that.
So KW4, these are the images that were first received. These are Arecibo images. This object was observed in, I believe, 2001. And what you see is that there are two satellites, that there are actually two asteroids. There is this primary one in the center, and then there is a satellite going around it. And these are also images. Oh, that was previously, I'm sorry. That previous was Goldstone image. No, this is Arecibo image. This is Arecibo image. I'm sorry. Can we go further?
I think we're looping it. So
we are looping it, I think.
Right.
Okay.
So
anyways,
the first one is Goldstone.
We received observations for both Goldstone and Arecibo, and we built a very large data set. And this was actually analysis done by late JPL astronomer Steve Ostra. This was his really prime catch, because for the first time you really imaged well this completely kind of unknown object, this binary. We realized how the binary asteroids look like. And so this is the three-dimensional shape model that is built based on those radar images. What you see is this primary asteroid, which is about 1.5 kilometers in diameter, and then you see a little satellite, which is about 500 meters, that is in orbit, orbiting around it. What radar managed to prove is that about 15% of near-Earth asteroids are actually binary asteroids, which is a significant number.
So that video looks very similar to what we have right here.
This is exactly
on the
it.
table.
This is the shape model of KW4, and this is our very high-tech one that breaks, and the real one doesn't come with a wire attached. So what you have here is how it looks like, and you see the primary, and you see this. This is a really rapid rotator. Okay. So this is another thing that radar showed us, is that when the asteroids are rotating very rapidly, this material, because it's a rubble pile, so it's kind of drifting off the equator. And we found that this is a typical shape, that this is a really typical shape of the rapidly rotating primary.
So it has a ridge.
It has this ridge. It has this ridge, and very often the rapid rotators tend to have a satellite. And what we actually found recently is that they can even have two satellites. And this one stays back.
So that's very interesting,
Yes, there are
because
two triple systems so far.
I had no idea that asteroids could have, they're basically moons, aren't they?
They are moons. These are moons, and they're 15%, as I said, of the near-Earth asteroid population, which have satellites in orbit.
So that
is very interesting, and that is really kind of another thing. So radar is starting to paint a picture of the population. It is starting to tell us, characterizing, we are starting to get statistical samples of like this. How many of them have moons? We also found that about 10% of the near-Earth objects are looking like peanuts, like two things stuck together. Maybe don't have a good model. This is actually main belt asteroid, but you kind of will get the picture. But you end up with these kind of two things stuck together, and they bring you another 10% of population.
That's interesting, because I have always heard that asteroids were like snowflakes. No two are alike, but it appears that you kind of have families?
Well, yeah, in general we're starting to find patterns, but however, as I said, we still have a way to learn, and it seems like every time we look, we find something new, and it never seems to surprise us. Currently, in our radar sample, we have 280 near-Earth asteroids detected. Obviously, not of them are imaged with high enough resolution that we get to build these three-dimensional shape models, but so far we have about 30 three-dimensional shape models that we reconstructed based on the radar data.
Okay. Here's another question. This time it's from Facebook. This is from Alex. The question from Alex is, what are you trying to learn from studying these asteroids and comets? What is the mission goal we're trying to find out?
There are several reasons really to why we study asteroids and comets. First of all, these are the like remnants of the early solar system history and the creation of the solar system some 4.6 billion years ago. And learning about asteroids gives us insight in the solar system past and also about planetary formation. We also want to learn about them because they had significant influence on Earth history, from geology to atmosphere to oceans to bringing organic material, water. Also, they could provide one day to be a very lucrative source of raw materials as we start to expand and colonize the solar system. And finally, we need to know the statistics and we need to assess the impact threat. So those are the reasons why we study asteroids and comets.
So knowledge can help us deal with a threat.
Exactly.
Okay. Here's a question. This one's from the chat. It's from W. Gameson. Why is this asteroid so spherical compared to the other more odd-shaped asteroids, meaning YU55, I guess?
Oh, YU55. So I have how potentially, this is another asteroid, this is not YU55, but it could look something like this. From what we are seeing still in those images, those images have 7.5-meter resolution, the ones obtained by Michael Nolan and his team at Arecibo Observatory last year. It appears that it's relatively symmetric. However, now when we image it with Goldstone and we have 3.5-meter resolution pixels, plus we'll have much stronger signal, so the details will be much more crisp. Maybe something that will surprise us is going to pop up, and maybe we're going to start seeing some maybe craters. Maybe it would be great if we see some detail. We also didn't cover, this is a slow rotator, so we think that it's rotating with about 18-hour period. And we didn't cover the previous set of data from Arecibo from last year, did not cover the entire rotation of the asteroid. It is possible that when it turns, maybe we are going to see some, maybe not completely spherical details. So I would hold my judgment until I see the rest of the data set and until we really don't map and see this asteroid from all possible angles.
But you don't see the same features as you see here. You don't see a ridge because this is a fast rotator, you said.
Yes, that is a rapid rotator, and this one appears to be a slow one. So obviously, I would be surprised to see anything similar to KW4. However, you know, it's always great to be surprised.
Okay.
So,
and we
but we are not
will be.
expecting.
All
Yes,
right.
so.
Here's another question from the chat, from many people, I understand. Can this asteroid influence the orbit of the Moon or Earth? And the opposite questions, will Earth or the Moon influence the orbit of the asteroid?
Well, that asteroid, it's so tiny that it has absolute no influence on Earth or the Moon. It's tiny. You can ask whether the aircraft carrier has influence, because it's about the same size. So it's not going to happen. While it's flying by, we have very good simulations of the flyby. So we know exactly how Earth and Moon will be influencing its orbit, so there will be no surprises there. And we will be continuing to monitoring it every step of the way and providing exact location measurements and incorporating it into the orbit. But this is not about predicting anything in the following 100 years. This is only going to extend our data, our orbital prediction capabilities in the future centuries. So for now, this is a very clear case, and there will be no surprises.
Now, you had one more video set aside for us.
Yes.
Another shape sort of
Yes,
model.
so here is another, this is another example why why we study, why radar is so valuable. And that is this what you're seeing on the screen. This is Nereus. Nereus is about 500-meter asteroid, and you're seeing its images as it's rotating radar echo. And Nereus has been flagged as a spacecraft target for several times now. It was originally NEAR spacecraft target, but NEAR ended up going to asteroid Eros. And it was actually Japanese spacecraft Hayabusa was supposed to go to Nereus, but they ended up going to asteroid Itokawa. It is one of the top 3%. It is literally top 3% most accessible near-Earth asteroids. And we built a three-dimensional model in order to help plan safer missions and things like that. So radar, us building three-dimensional shape models of near-Earth asteroids ultimately is going to help NASA build safer missions, and we are kind of supporting, in a way, any spacecraft missions that would go to asteroids that, if they were observed, with a radar. And so, if we can assist and help, that's really great for us.
But it's interesting. I think your, I guess, in a way, goal is to be able to get enough information to be able to have as much information as you would get when you have a spacecraft fly by an asteroid like this, being able to see so much resolution, what sort of surface features. And with these new techniques, you're beginning to actually be able to see surface features.
Well, it's really, with a radar, we can get spacecraft quality data, and one of them are shown actually on the screen. I don't know if our viewers are seeing it, but this asteroid here, 1999 JM8, this is really a radar put probably more than 10,000 pixels on this object. And obviously you start, the features like large craters and irregular shape start to pop out. Something like this was previously only we were able to do only by spacecraft flyby. And yet this asteroid, these are actually images from 1999, when this asteroid was about 22 lunar distances away, and we still got these amazing images. So radar has incredible capabilities, and currently we image about 20 to 30 asteroids per year, but this can be very much expanded, and we can really learn about this population from kind of comfort of our home.
Right, being sort of an
earthbound
armchair observer, you get to stay here and see perhaps not quite as much as you would see on a flyby, but this technology is at its infancy, isn't it?
Yes, this is radar planetary radar science. It is relatively young field. We've been getting these kind of routine radar observations maybe only since mid-1990s. So there's still a way to go, and we have just kind of scratched the surface with it. Obviously, spacecraft missions there's no such a thing as a replacement for a good spacecraft mission. So I'm looking forward radar helping raise spacecraft missions of the future.
So here you are, you're observing these with radar, you're bringing back models and learning about the various sort of categories and shapes. What do you ultimately want to do to be able to see with all these observations that you're making right now?
Well, we're trying to take really a snapshot of the population, because the shape of these objects, they're really telling us about their origin and about their future. The shapes of the asteroids are very also important for long-term orbital calculations, and so we kind of build this picture of one very frequent guest of our solar system. Well, not even guest, resident. This is there are a lot of asteroids out there, and we are building this very detailed picture.
And to look at the future uses of all of these things, that you'll be able to kind of understand which shapes indicate what could be the type of asteroid it might be.
Yeah, it always generates new questions. You see binary and you wonder, well, okay, how did it get that moon? What is the mechanism? How can it get the moon? And then there are theories floating about how an asteroid can get a moon. Then how do you get two moons? Which one came first?
Right.
This tertiary came from the primary, or the second moon split in half. Or so all these objects, near-Earth objects, they really originated from the main belt. So this is between Mars and Jupiter. There's a big debris field, and then under influence of the gravitational influence of large planets, of Jupiter and Saturn, some of these guys get nudged toward the inner solar system, and then they become these near-Earth asteroids, and there are about more than 8,000 of them. So you start asking questions. Okay, did this object had satellites already back in the main belt, or it acquired them? There's a lot of empty space. The chances that the primary would just pick up the secondary are very, very, very kind of small. But every time we see something like that, you start asking questions. Or you have these contact binary asteroids, and again you ask questions. Were these originally two moons, or this was a single piece, then there was a close planetary flyby that kind of moved them away? And this spurs incredible amount of theoretical studies, and dynamicists have a whole bunch of work to try to explain what are we looking at. You know, at what point can you fission off an asteroid? What are other mechanisms possible? So with every new object, new questions arise.
So here's our last question, and it's from our chat. It's from Himono. How much do you think we can learn from the information we'll gather from this asteroid?
So what are we going to learn about this asteroid? Well, the images are going to be...
This will be the best ever, won't it be?
Well, it is going to be remarkably good. I really can't wait to see the images. I can't wait to learn more about it. We need to check whether this rotation period is really 18 hours. That's something, for instance, we're interested. We need to see, we would really like to characterize it as much as possible and learn kind of about its past and about its future.
So the big day, you begin on Friday, but the big day for all of us is...
Yes, it's going to be November 8th.
November 8th.
That's a close approach, but no worries. Absolutely, Earth is safe.
No worries.
So,
well, Marina, thank you so much for joining us. In a little bit, we'll be joined by Don Yeomans. But first, we're going to look at a video that talks about, well, we call it the CSI. It's an entire team that takes upon themselves to keep an eye out on near-Earth objects out in space that has a potential threat to us here on Earth, and that's their job. And here's the video.
What do we have here? Is that another PHA?
Take a look at the Palermo. My guess is that this body is an Aten.
Do we have a size?
Got to be in the 300-meter range.
Let's get on this. You can think of the Near-Earth Object Program Office as sort of a CSI unit. We discover these objects, we try and determine what they're made of, where they're going, and just how dangerous they might be.
In December of '04, one of the new discoveries was an asteroid that later became known as Apophis.
It's an object about 270 meters long that's going to make an extremely close approach to the Earth on April 13th, Friday the 13th, 2029.
This object isn't a source for concern now, but back then it had us worried. So this is a representation of the Earth and the orbit of the Moon and the uncertainty region of Apophis. All of the points on this line are possible locations for Apophis, and any one of these dots could be the actual asteroid.
All of the numbers that we were seeing were well beyond what we had seen before, and the threat level as a result was elevated. The impact probability for a collision with the Earth in 2029 reached the 3% level, 3 chances out of 100 that it would hit.
When we saw the impact probability rising, we put out calls for others to look in their archives for images of this asteroid at previous dates.
When we got additional observations from the optical telescopes and when we got additional radar data, the threat level went to 0 in 2029 and only left a slight possibility of an impact in 2036.
There is a possibility that after it goes by the Earth, it may pass through a small doorway or keyhole, I call it, and be deflected by the Earth's gravity into an orbit that would be about 7/6 of a year.
The Earth would go around the Sun 7 times, the asteroid would go around the sun 6 times, and they would meet up at the same place at the same time on April 13th, 2036.
It will be important to look at this asteroid in the year 2013. We hope to see it with radar, and then hopefully we will confirm that the asteroid will not pass through that keyhole. That should allow us enough time, if we unfortunately see that it is going to the keyhole, perhaps to mount some sort of mission to the asteroid to deflect it. And all we have to do then is deflect it away from that keyhole.
We don't let down our guard, not even for a day. It's our job to monitor the inner solar system and make sure that none of these objects are getting dangerously close to the Earth.
We're back now, and we are back with the familiar face, Don Yeomans. He's the person you just saw in that video. He's the manager of the NASA Near-Earth Object Program Office. And that video talked a lot about Apophis, and that seems to always be of concern to a lot of people. Can you give us an update on it?
Sure. Apophis is the poster child for near-Earth objects. It's the one that's always mentioned because it's going to get very close to the Earth on April 13th. Friday the 13th, 2029. So, but it's not going to hit. We know that for sure. There's still a very small chance that it could hit in 2036, but that's 1 in 250,000. And if we get the radar observations and optical observations that we expect next year, late next year, I think it's fair to say that we can rule out that 2036 possibility as well.
Even that. Okay, well, everyone seems to be still concerned about YU55. We still are getting these questions. Is there a chance that this asteroid could change course and become an asteroid that's headed our way and come closer?
No. We understand its orbit very well. We understand what bodies are nearby and are gravitationally nudging it. So we take all of that into account as we integrate its motion forward in time. So there's no chance of any object, unseen object, getting in its way and perturbing its course. So it's completely safe. There's no chance of an impact.
I think we have an email question from Z Epsilon, I believe is the handle. What gravitational factors or other could probably alter its repetitive trajectories enough to become a serious threat to either the moon or the Earth?
Well, that's a good question. As this object goes around the sun, of course, it's perturbed when it gets nearby a planet, Mars or Earth or the moon. And it does nudge its orbit just a bit, changes it. So as we go forward in time or backwards in time, these gravitational nudges by nearby bodies do affect its orbit. And once we have the radar data in hand that Marina talked about, we'll be able to project its motion forward for several decades and see whether there's any interesting close Earth approaches.
So through its lifetime, they can alter and change a bit?
Oh, yeah, very much so.
But not dramatically?
Well, if they get very close to an object, a massive object like the Earth or Mars, it's not going to be dramatic, but it will change its course substantially. I mean, that's how these objects got into the inner solar system in the first place. It's gravitational nudges by Jupiter and Saturn that sort of pushed them slowly into the inner solar system. Okay.
Well, now we have questions for you on Ustream. And I believe this is from Unslave Me, is the handle. How can you guarantee its orbit will not change due to unknown circumstances?
Unknown circumstances, I see. Well, again, we know all the objects that are nearby, all the massive objects, the Earth, the Moon, Mars, Venus, all of these planets, we know where they are as a function of time. We know how massive they are, so we know what kind of an effect, a gravitational effect, they can have on this object. And if there's an object there that we can't see, I can't imagine what it would be, but it would be affecting the motion of the Moon, and it would be affecting the motion of the Earth, and we don't see that either.
Okay. TOFEM26, can we ever pull an asteroid into orbit? I guess that we sort of had a question like that.
Pull an asteroid into orbit around the Earth? Well, actually, we've been studying, there's a group at JPL who does advanced planning and studies, sometimes out-of-the-box thinking, or purple pigeons, as they're called. And that was one of the concepts. Could you go out, grab an asteroid, and bag it, literally, and bring it back into an orbit that would be then around the Earth. And yes, you could, if you used solar electric propulsion and the asteroid were small enough. It would only be the size of an SUV or something like that. You're not going to go out and grab a huge asteroid and bring it into Earth orbit, but you could grab a small one.
So catching asteroids.
You could do it.
It's an actual idea that folks are working on.
It is indeed, yes.
Which I guess should bring us on to another topic. Why are we so interested in asteroids? I mean, what value do they have to us?
Asteroids.
Good subject.
They are indeed. They're among the smallest objects in the solar system, but they're among the most important. They are the least changed objects from the origin of the solar system. So if we wish to understand the chemical mix and the thermal environment from which our solar system, including the Earth, formed, we'd like to study these asteroids. They brought to the early Earth much of the carbon-based materials and water that allowed life to form. Subsequent collisions, once life did form, punctuated evolution, allowing only the most adaptable species to go forward. So in a sense, we owe our very creation and our position atop the food chain to near-Earth asteroids. And for the future, we could mine them. They have precious metals, platinum group elements. Some of them have water resources in the form of hydrated minerals. So when we get out in the inner solar system and build habitats, we're not going to build them on the ground and launch them into space. We're going to go up there and look around for raw materials. So they're important for our future. And then, of course, if we find one with our name on it, we're going to have to track it and deflect it if we are to have a future.
So we have a couple of images and videos. I mean, a lot of people don't realize how common asteroids and meteors and, are all around us. And there's a couple of images we have from Peekskill that we can actually show. That here is an event.
Oh, yeah. This was October 9th, 1992. Friday night, and a lot of people were out with their video cameras filming high school football, and that was a Volkswagen-sized object that came into the Earth's atmosphere and broke up into 70 or so different pieces, and one of the pieces, about the size of a football, there it is, landed in Michelle Knapp's 1980 Chevy Malibu. The insurance company said, forget it, we're not paying for it, it was an act of God. Michelle turned around and sold the car and the meteorite for $69,000. So
the only car ever to be hit by a meteor.
Well, it's one of the only ones that got hit this badly, certainly.
With the culprit right there.
Yeah, that's a good-sized meteorite.
So people don't realize that fireballs happen all the time.
Oh yeah, the Earth is inundated by something like 100 tons of interplanetary material daily. Most of it's in the form of dust particles or sand-sized particles, and that's what you see when a particle that size comes into the Earth's atmosphere. You see a shooting star or meteor, so you make a wish. Something the size of a baseball or a basketball, they come in daily and they form fireballs. Something the size of an SUV, the type that created the Peekskill, they come in a couple times a year.
And what about this one?
This is Meteor Crater near Winslow, Arizona, and this was formed about 50,000 years ago when an asteroid, solid iron this time, about 30 or 40 meters in diameter, slammed into the desert floor, creating this enormous meteor crater, as it's called. I know that because I know it was iron, because around the edge of the crater, there's all kinds of iron meteorites that were picked up. In fact, I have a couple.
Oh, so all of these are very, very different.
Yeah.
And if it's iron, that's a resource.
That's true. We could utilize the resources in space, and then there's platinum group elements. But you made the point that they're very different. The diversity of asteroids is enormous. When I was in school, mind you, that was the Middle Ages, asteroids were whirling rocks, just that's how we thought of them. But now we know that asteroids can be ex-cometary fluff balls, wimpy material that you could break apart in your hands. They can be rubble piles that are held together by little more than their own self-gravity. They could be shattered rocks like Eros. They could be rubble piles like Itokawa. And they could be slabs of solid iron, like this one that formed Meteor Crater.
Well, I'm sure the chat group is screaming now because I haven't answered any questions, but here we go. Let's take a few more. Can YU55 generate gravitational forces that could cause earthquakes?
No. In fact, YU55, although it's getting close to the Earth for an asteroid, it doesn't have a significant effect on the Earth's its gravity doesn't have a significant effect on the Earth. In fact, I think it's fair to say that you and I, sitting here, probably have a greater effect on the Earth than this asteroid will have. The tidal effects goes as the inverse cube of the distance to the object, so it's you'd have to have something very close and very large, like the moon, to cause tidal effects.
All right. Mr. Rocky Astro wants to know, why do we not destroy the asteroids? You never know if it will fly past Earth again, but in a dangerous way.
Well, the proactive strike.
Get rid of it.
There you go. Well, it's easier to simply monitor their motions, compute their orbits using the radar and the optical data, and predict their motions a couple of hundred years into the future. And if any one of them causes a problem, or potentially causes a problem a few hundred years or tens of years into the future, then we could mount a mitigation campaign to do something about it. But to proactively start going after benign asteroids seems a little
mean
and wasteful of resources, and,
okay.
and not very smart either.
All right, here's one. What is the difference between YU55, Elenin, Nibiru, and Planet X?
Well, Nibiru and Planet X is just internet nonsense, I'm afraid. They don't exist. There are lots of sites out there on the internet that claim that Nibiru exists, Planet X exists, but there's no evidence that either one of them exist. Folks say, well, they could be dark. They could be dark? Yes, they could be dark, I suppose, but they would still have a gravitational effect on the planets and the asteroids, and we don't see that. So Nibiru and Planet X, they don't exist. It's just that simple.
What about YU55 and Elenin?
Comet Elenin did exist, but it went by the sun, and as about 2, 3, 4% of comets do, it simply broke into a cloud of dust. These comets are very friable, very fragile objects, and if they get near the sun, a gas pocket could explode and just blow them apart. So Elenin no longer exists as a comet. It exists as a cloud of dust that will go around the sun and exit the solar system fairly soon. But Elenin is no longer. Nibiru and Planet X never were.
Okay, here's another one. If an asteroid is headed for Earth, can observatories around the world see it? Or does NASA have the exclusive of knowing when an asteroid is close?
No, we don't have an exclusive. The NASA program to find near-Earth asteroids is designed to find the majority of the large ones, and we have, about 93% of the objects larger than 1 kilometer have already been found, and we've tracked their motions 100 years into the future. None of them pose a problem. Now, Congress has asked NASA to look for the 140-meter and larger-sized objects and find 90% of that population, and we're 35% there already, and none of those objects pose a threat. So NASA is taking up the challenge to find and track these objects, and we will continue to do so.
Last question on this page. Is there a plan to warn the public of an impact?
Yes, of course. All of the close approaches and the objects for which we cannot yet rule out an impact are posted on our webpage immediately. There's no effort to hold anything back from the public. We couldn't do it anyway. I mean, you can't keep scientists quiet. They're just...
You heard it from a scientist. All right, here's one. Could a huge asteroid cause Valles Marineris on Mars, and also causing the Tharys bulge material from gas piled up on Mars's surface?
Well, that's a good question. In fact, most of the craters on Mars, and especially the moon, are due to old asteroid impacts. We used to think, well, 100 years ago, it was thought that all of the craters on the moon were volcanic, but only a few of them are. And most of the craters on the moon are impact created most of the craters on Mars are impact created. Sometimes when the impact hits, it will trigger a volcanic event, and sometimes volcanic events that occur on their own, but most of the craters are in fact impact.
One more question. It's a sort of spin-off of our earlier question. It's what would be achieved by bagging an asteroid on Earth's orbit? What we were talking about earlier.
Yeah, why would you bother?
Why would you bother?
If you'd like to, President Obama in April of 2010 suggested that the ultimate goal for human exploration is Mars. But that's a tough trip for humans to make, a couple of years. So you'd like to try something simpler that's further than the moon, but not as far as Mars. So you'd like to try an asteroid. Use an asteroid as a human exploration target as a sort of a stepping stone to Mars, because it's easier and you can get there more quickly and return more quickly. So then you have to ask yourself, what would you likely want to do before you attempted such a mission? One possibility is you might go out and grab a small asteroid, bring it back into Earth orbit so it could be studied carefully. Are there platinum group elements there that are worthwhile? Are there water resources that might be mined? What kind of a structure would you expect in the inside? How are they put together, so that you would learn a great deal about that type of asteroid before you sent humans there, and you would understand that type of asteroid in case one of them in the future would be on an Earth-threatening trajectory.
And would that be very, very easily doable at this time? We've done several flybys of comets. We have Vesta captured, Dawn captured into orbit. I mean, we've sort of gone almost all the little baby steps towards that.
Right. Well, would it be easy? No, it wouldn't be easy. It would be an engineering challenge, and you could question whether it would be worthwhile. It might be simply easier just to go to an asteroid and use that as a stepping stone rather than trying to bring a small asteroid back to Earth orbit. But the platinum group elements on the Earth are mostly mined in South Africa, and it's a limited resource. So if one day in the future we run out of the platinum group elements on Earth, we may want to go up there and mine them in space.
Okay, here's another question on the chat. Can coronal mass injections impact the orbit of an asteroid?
Well, coronal mass ejections from the sun are charged particles that are periodically belched out in the interplanetary space. But they are charged particles, so they have very little mass, very high speed, but very little mass, and so they wouldn't have they would have only a very negligible, immeasurable effect on the asteroid's motion.
Well, here's an interesting one. This is from Disclosure 2008. What is the strangest thing you've ever come across with asteroids or comets?
You hasten to add. Well, I think the fact that comets seem 2 or 4% of them just spontaneously disrupt for no apparent reason. They don't necessarily have to get close to Jupiter or the sun to simply break apart into a cloud of dust. They just do this. So why do they do this? Elenin did this recently. It's possible they ran into a bit of space junk, but it's not very likely. It's probably more likely that they gas jets spin the object up, much like an asteroid is spun up, and then they just sort of fly apart because they're so friable, so fragile. So the behavior of comets is very intriguing.
So that's not uncommon to be tracking a comet and watching it and for it to suddenly disappear.
Yeah, right. In fact, we've had that happen on a
mission.
On a spacecraft, a potential spacecraft mission. Comet Bothan was to be the target of the Deep Impact follow-on mission, and Comet Bothan never showed. So we switched targets and went to one that did show.
Okay. One more question regarding YU55. How close will the asteroid get on November 8th? And we're told it's about, what, 9/10 the distance between Earth and the Moon. Is that considered very, very close? I mean, it's almost as close as the Moon.
It's closer than the Moon, actually.
Yeah.
It'll get within 201,000 miles of the Earth's surface, 51 Earth diameters, Earth radii, excuse me. So, yeah, it's close. You'd expect an object of this size to get that close every several tens of years. So, this is a great opportunity. Something this close, something this large has not come this close since 1927. Or is it 47? Anyway, it's a few tens of years. So, yeah, this is close for an object that size.
We're told 1976.
76. That's good. Thank
Okay.
you. You corrected me. That's good.
Somebody told me in my ear. That's okay. Okay. Could you guys speculate a little on the insides of asteroids?
Well, that's a good question. We only see, with optical and radar, we only see the top layer, of course, and so you have to ask yourself, what is the inside? And that's why missions, future missions, might want to use seismic instruments. They might want to use penetrator devices. If I were to guess, I would say some of the largest asteroids, like Vesta, are what we call differentiated. That means they're layers. They have a core, they have a mantle, and they have rubbly surface because they get impounded by other asteroids, smaller asteroids, over millions of years. And some asteroids are simply ejection fragments from previous impacts of larger asteroids. So you get, so one of these layered objects can be broken apart, and so now you have bits and pieces of the inner core, which might be iron. You'd have bits and pieces of the mantle, which would be silicate rock, perhaps, and you'd have bits and pieces of the outer rubbly layer, which would be rubble piles. So you might expect asteroids to be formed in that manner.
Well, he's wondering, could there be crystal caves?
Crystal caves? I have not a clue, to be honest. I doubt it. But
that would be pretty.
Yes, it would.
All right. The same email person, Kenia, asked if a sinister and evil agency or corporation would decide to send a booster rocket into space that would put an ion drive on this asteroid the next time it passes, could such a sinister agency slowly nudge such an asteroid or a similar one towards the Earth for a horrific impact?
Yes. That's
sinister.
Interesting concept. In fact, that very concept, I remember a debate between Carl Sagan and Edward Teller, the father of the H-bomb, on that very topic.
Really?
If you could go out and start moving asteroids around, could you find a benign asteroid and put it on a trajectory that would actually hit Earth? Yeah, you could, but why would you? It would have to be a spacefaring nation. It would have to be someone completely out of their gourd, and there's a whole lot easier ways to cause mass destruction on Earth than trying to target an asteroid to hit somewhere on Earth.
So too much effort for the evildoer.
And the evildoer could do a lot better with something
Something
simpler.
else. All right. Can an asteroid ever orbit Earth instead of hitting it, or just like a small moon? So can an asteroid, I guess it would be captured into orbit, just like the moon?
It could happen. There are no asteroids in Earth orbit at the moment. Occasionally one comes by close enough and slowly enough so when the Earth is going around the Sun, it is temporarily captured around the Earth, but not permanently. In order to have a permanent capture, you'd have to have what we call a third body interaction. It would have to come by the Moon or Mars and be its orbit adjusted just so that it would be in a very Earth-like orbit and then be captured as it very slowly drifted past the Earth. So it's very tough to do, not impossible, and occasionally an asteroid does get into a temporary Earth orbit.
So what about Trojan asteroids?
Trojan asteroids, and there is one, Earth Trojan, actually lead or follow the Earth around the Sun. So they're not actually in orbit around the Earth or in orbit around the Sun, but they're in an orbit identical to that of the Earth, or nearly identical to that of the Earth, so that it keeps pace with the Earth either ahead of it or behind it. And the Trojans are named after the Jupiter Trojans, and there's a cloud of Jupiter asteroids that are leading Jupiter around the Sun and following Jupiter around the Sun. There's thousands of them.
Another chat question, is there an asteroid heading towards, if there is an asteroid heading towards Earth, is there anything we can do about it?
Oh, sure. If we find it early enough and we know its orbit well enough, which is some of the goals that NASA has, is to find them early, and find them early. Those are the three important goals. Then and the most likely impactor would be a small one, because there are a lot more small ones than there are large ones. So one of the most effective and robust techniques for deflecting an asteroid are simply to run into it with a spacecraft, as we did with the Deep Impact spacecraft back in 2005 with Comet Tempel 1. So we have the technology, we've demonstrated the technology that we can actually run into an asteroid with a spacecraft, slow it down just enough so that in 10 or 20 years, when it was predicted to hit the Earth, it wouldn't.
So sending a spacecraft out not to just visit it, but actually give it a little bit of a nudge.
Give it a nudge.
All
and
right.
if that doesn't work, give it another nudge.
Okay. Well, Don, always a pleasure. And the big event happens on November the 8th. YU55 is going to fly by pretty close. Not quite the little closer than where our moon orbits, about 9/10 the distance, and it's a 400-meter asteroid, so that's about the size of an aircraft carrier, so nothing too tiny. So people will be able to see it that night. If you have a telescope, I'm told you said at least, what, a 6-inch telescope?
Yeah, Marina said 6 inches, which is right, or larger. And you can get the coordinates that you need, either Sky and Telescope or even our own Horizon site here at JPL. It's ssd.jpl.nasa.gov.
One more time.
SSD,
Okay.
Solar System Dynamics, .jpl.nasa.gov.
All right, so you can look it up. You can see it yourself November 8th, the night of November 8th. You can actually get the coordinates so you can spot this asteroid going by, and it'd be pretty fast?
Well, it's going to be moving just under 9 degrees per hour, so if you see it in your telescope, you'll see it move.
Okay.
But it's not going to zip across the sky.
All right, so should be an exciting night.
Yeah.
All right, Don, thanks for joining us, and thank you for joining us for this Ustream chat on YU55, and we hope to do it again sometime. Take care.